to infinity of this term, of course you can open the summation to two different summations. One for negative range of n, so n equal to minus infinity to minus 1, and positive range of n. This is how the summation works, of course. The key point, which I will use it for the next step, is that this negative range can be converted or can be written as a positive range if I replace all of the n I have with minus n. Mathematically, it's possible to prove this, so it's correct. However, for this pink area, I can change the summation from minus range to positive range. So from n equals to 1 to infinity of c of minus n. So I replace all n I have with minus n e to the power of I minus n omega t. And now I have the summation which both ranges are 1 to infinity. So I can put them under one summation of 1 to infinity, okay? So just keep in mind that this is always correct mathematically. I will not prove it here, but it is possible to do or use it. So now I have to go to board number 7. So I will start, or I will use what I have here. So I have 1 over 2. And now, instead of this range of summation, I want to use only positive range. So it will become plus the summation of n equals to 1 to infinity of Cn e to the power of I n pi over 2 times t plus c of minus n e to the power of minus I n pi over 2 times t. And of course Cn, we have a sign, so I can put them here. So this is equals to 1 over 2 sine of pi over 2 n divided by n pi I just replace the Cn we had before here and C of minus n here. Now again here I want to use some math formula. Again, I'm not sure if you have or you can remember it from before. That's we should know that sine of minus x is always and always the same as sine of x. So I write it down here. This is always correct. So now it means that this sine of minus pi over 2 times n is exactly the same as sine of pi over 2 times n. So no matter what is the value of n, the formula is always valid. So what I can do, I can make the factorization of these because these are the same. So it will become 1 over 2 plus the summation of n equals to 1 to infinity of
But it is the sine of minus x, isn't it equal to minus sine of x?
That's what you said.
oh yes, it should be minus, sorry. It should be minus sine of x, thank you. Yeah, I think I have a minus in the slide as well, at the top there. It is minus, minus is in front of equality, minus sine x. Yeah, thank you, that was a very good point. That was my mistake here. So and again it will become, let's write it here now. This is the same as minus sine of pi over 2 times n. With this minus and minus make it plus, so I can write this as a plus and plus. And now I can make the factorization. So it will become sine of pi over 2 times see if I missed anything before I go any further. No, for now it's good. Then plus e to the power of minus I n pi 2t. Okay. Let's see what we can do from here now. I have sine of pi 2n. Let's look at the Euler formula and see if we can use one of those here. So I have e to the power of I n pi 2 minus plus. Actually, if I can create some sort of 2 here, then I can use the cosine format. Am I right?
Yep.
Okay. It is possible. How I can do that? If I multiply this by 2 and divide it by 2, which is technically I multiply by 1, so mathematically nothing is changed. So now this can be written as 1 over 2 plus the summation of n equals to 1 to infinity of sine of pi 2n over n pi, and then e to the power of I n and I will bring this 2 here. I have a 2 which I can either put it here or I will put it down here, because both are possible again, just how you rewrite it. Now this one will become cosine. So then this is equals to half plus summation of sine. I will show you why I decided to put this here. Just give me a second, but I will show you. Here, n pi over 2 times cosine of n pi 2t. Actually, this can also be written in this format, and I just wanted to have the same format of in the parentheses. That's why I did it. But now you can see that the complex form, we converted that to the real format. And then you can do the approximation or rough approximation for the function. I have, I think, the solution in the slides as well. Yeah, it's here. Yeah. Any question?
Why wasn't you put the n down so you had it up to the same?
I just wanted to have a better, nicer looking of this
Okay.
here.
So it's
But also, it is possible to rewrite it in some other way. I haven't done it in this example, but let me show you. If I write the sinc function here, just okay. I don't know if you are familiar with this function. It's called the sinc function. The sinc function, which is this way, I haven't used it here, but it's possible. The sinc of x is always sine of x divided by x. And now you can see this can be also written as a sinc. And how does this sinc function look like? It's something like this. I don't know if you have seen it before or not.
No.
But it is possible to use it. So if I want to rewrite it again, I can replace this with sinc of pi over 2 times n. Again, I have not done it here, but you can do that. That was also another reason. here. So far you have learned that how this function can be approximated with these formats, this exponential format. As I mentioned earlier, I think it was in the first or second slides, this can be rewrite as a sine, cosine, or harmonic oscillation format as well. How we do that? This is the line you have to use it to convert this exponential format to harmonic oscillation format. Based on what you see here, when you have it like what is here, it's equivalent to A0 plus this summation. What is A0? A0 is the same as C0 you obtain for the Fourier series coefficient. So when you have it, you can directly put it here. And then, of course, you obtain Cn as well. And 2 times the absolute value of Cn is An, which is here. And then cosine of n omega t. Omega is what we obtain, frequency. So it's 2 pi divided by capital T. And plus phi. This phi is always the argument of Cn. Again, if you don't know what's argument, I have it in the next few slides and I will explain it there, what I mean exactly by argument. But phi is always angle. So the argument of Cn would be always some sort of angle of 0 to pi, pi over 2 or something. Can you remember argument from before? But anyway, I will repeat it for those who cannot
It's the
remember.
argument part of a polar form of a complex number, right?
Yeah, yeah. For any complex number, of course, you can also obtain argument.
But is that 5?
Yes, I think in the Greek they call it phi.
Oh, okay. Because it just looked like it's Ö.
Yeah, it's like a Danish alphabet, I know.
Yeah.
Okay. Let's have some definition here. The number sequence Cn of the Fourier series always called X spectrum. So if you heard X spectrum, this is what does it mean? It is the sequence of the number sequence of Cn. And in polar representation, the Cn can be written in this way, and we use that to define this two-sided amplitude spectrum and two-sided phase spectrum of your function or signal. What is two-sided amplitude spectrum? It would be always and always absolute value of Cn for all range of n. And the two-sided phase spectrum is this argument, phi n, for all range of n. A question which may come in mind is that why it's called a two-sided, and if in one of the exercise I see one-sided amplitude spectrum, what's the difference between them? Any idea?
Only positive numbers.
Or maybe only negative? Yeah, it's called two-sided because you have both negative range of n and positive range at the same time. When I ask, or in exercise you see the one-sided spectrum, you can only focus on the positive n, I mean 0 and more, or you can focus on the negative side, 0 and less. And that's, it's called one-sided spectrum. Amplitude spectrum, phase spectrum. Something which is good to know and remember is that when you plot, because it's possible to plot both amplitude spectrum and phase spectrum of a signal, amplitude spectrum always and always, this is an example, should be mirrored with respect to y-axis. So when you plot it, you have to look at for this mirroring, and if you cannot see that, it means you did something wrong. So amplitude spectrum should be always and always mirrored with respect to y-axis, and phase spectrum should be always and always mirrored with respect to origin. And that's why you can see this is up, up, down, and down, down, up, because it's the mirroring with respect to only origin point. Again, you can use this to check your computations and plots. Let's, for this example, which I had it before the break, plot the amplitude spectrum and phase spectrum. I will do it, the results are here, but I want to do it on board. 0. Here, I consider again two other cases. If n is an even number and if n is an odd number. Sometimes the result of these two becomes 1, then we can combine together. But now here I know that they are not the same. That's why I have these two categories. N is not 0 and even, and f is not 0 and odd. What was the formula of Cn? Again, it's here. This is the Cn formula. If n is an even number, like 2, 4, 6, minus 2, minus 4, let's see what it will look like. If n is 2, 2 and 2 cancel out each other. And what is the sign of pi? 0. So 0 times anything is 0. So for n equals to 2 is 0. Let's look at n equals to 4. It will become 4 and 2 cancel out. So sign of 2 pi is still 0. If you try for n equals to, for instance, minus 6, again this becomes 0. So for n even, it will be always and always 0. How about if n is odd, like 1? We have sine of pi over 2, which is 1. 1 times 1 over pi. Okay, so for n equals to 1, it is 1 over pi. For n equals to 3, it will become sine of 3 pi over 2, which is minus 1? Minus 1, yes. So it is minus 1 over 1 over n pi, 3 pi, minus 1 over 3 pi. Yes, I think. Let's do for minus 1. For minus 1, it is minus 1 over minus 1 pi. Am I right? N is minus 1 and sine of minus pi over 2 is minus 1. And again, yes. If you do it for other values, you can see. I want to in scenarios like this, you should find the general format for all possible cases. So that's why I'm trying to show you this one here. So n of minus 3 pi over 2 is 1. And then minus 3 pi. Okay. What's general formula or relationship between these? This is 1 over pi as well. And this one is the same as this. So if we do the plot for n equals to odd for now only. So if it's 1, it is 1 over pi. If 1 over pi is here, for instance. This is 1 over pi. For minus 1 is also 1 over pi. So I see the mirroring. For 3 is a little bit less. So maybe here and here. For odds is 0. So here I can put 0 and 4 is 0. 0. And minus 4 is 0. At 0, this one should be 1 over 2. So 1 over 2 maybe is here. I see the mirroring with respect to y-axis. And here, the general formula we can write for that can be written as 1 over pi, absolute value of n. Why? Because if you put different values of n here, you get exactly what is obtained, what you have for the plots there. In exam or in exercise, when I ask you to do this type of plots, to write this, that's also fine. Maybe a question which may come in mind is that how we can do these plots in Maple. Just a second. I go here. To learn. I think I have something there, and that's good to look at it. It's not the Maple file, so I can show that. Oh, it's extra notes. The reputation of Fourier series. Yeah, reputation of Fourier right here. In this file, we have some sections which there are some examples, and if you look at them, you can become familiar with plotting amplitude spectrum and phase spectrum. Oh, I think this is now. Oh, here is the codes you can follow. First, read the example, understand it, and then you can, here you see how we did or how we tried to plot the amplitude spectrum with Maple. And I think if you will go down, we have something for phase as well. Oh, it's phase here. So I highly recommend and encourage you to look at these examples and become familiar with plotting both amplitude spectrum and phase spectrum in MATLAB. Sorry, Maple, not MATLAB. Yeah. But again, if you prefer MATLAB, it's also possible. But I have the source for Maple here. Yes?
And is it 3? We have minus 1 divided by 3. I. All the blocks, why above
Because we have the absolute value of Cn for amplitude spectrum, and that's why here I put the absolute value here as there, because this is only Cn and not absolute value of Cn. So, but here we plot this one. This is the plot for absolute value. That's why -1 and I mean this minus and minus here in the plots are positive values. That was a good question. Okay. Let's look at the phases. That was the amplitude spectrum. And of course, you can do the phase spectrum as well for different range of n 0, odd or even. Which n is 0, the phase would be 0 here. But why? Let me show you. We have C0, which is half. And now you need to find the argument of half. So if I have this plot here of sine and cosine, axis. This is the cosine axis, and maybe this is sine. Okay. When we have the argument of some number, like half, plus half, we are, let's not put cosine. Here is a real axis, let's call it. Half is somewhere maybe here. And then, in order to find the argument for that, we start in this axis, and we should turn or move anti-clockwise, which here, we don't move to do any turning. Why? Because the half is on this axis. So the amount of angle would be 0. And that's why the argument is 0. For instance, if n is 2, we are here for Cn. So we have sine of pi, which is 1. So I have 1 divided by 2 pi. So I need to find the argument of 1 over 2 times pi. And pi is 3 point something. And 2 times 3 point is the argument of 1 over 6 point. And then, again, this is some positive value. And the argument would be, again, some point maybe here. It still would be 0. And that's why for want to have a general formula for that, you can put it like this one and do the plot. I don't expect that you do the plots manually, but if you want, it's up to you. I prefer that you use Maple because you can save time by Maple. And you can see the mirroring with respect to origin here as well. So we did everything correctly. Yes?
Why, when you explain it like that, like, if I should think about it, I would say that for the odd numbers,
Do you think for odd number would be 0?
if you do it like on the real axis.
Okay,
Isn't
let's
it
let's
still
do it
correct?
one case together. Okay? Assume n is 3, like what I have here. Okay? If n is 3,
I get it over there. I know why it's not 0. But when you explain it like that,
then I can show you here as well why it's
Yeah.
not. Because it is n is 3,
yeah.
and the sine of 3 pi divided by 2 is -1. Am I right? And -1, so you have -1 over 3 pi. So I have a number which is maybe, I don't know, here, somewhere in the opposite direction.
I get it.
Okay? And then in order to reach here, you have to turn pi degree to reach to this location. And that's why I have a line or this lollipop which goes till high. Any other question here? Yes?
This is only for the function example f of t is equal to 1, right?
No, this is for f of t we had earlier. This is for this one.
Yeah.
This is the two-sided phase spectrum and amplitude spectrum for this f of t. The one we worked on it from today, I mean earlier today.
Yeah, and in the time we measure is f of t is equal to 1 for this example, right?
Can you, f of t equals to 1?
Yes.
No, we did all computation for this one.
Yeah.
Why, for this one, for this f of t, you can see it has a function somewhere 0, somewhere half, another half, also 1 for -1 to 1, okay? And based on these, we obtained C0 as half and Cn as this function. So in order to do the plots, I'm using these computations. So all the plots I did are for this f and not only f of t equals to 1. I don't know how you can see it only for f of t equals to 1, but it's not correct. Yes.
I think it's because on the tau you have I of you take the f of t and
Here?
put it to 1. Yeah.
Oh,
I think it's because of that and you point out on
now I see your point, because here in this particular example, we had the function f equals to 1 for this range. Am I right? Yeah. But it's not always the case. In this particular case, it was 1.
Yeah.
But maybe you can have for -1 to 1 equals to function t. Okay? And then when you do the plots are for that special one.
And we'll get a new coefficient.
Yes, of course you do all C0 coefficient, all new Cn coefficient, and so on. Yeah. Now I see the question. Sorry. Okay.
And then this with the argument and the
This is the argument. Yes.
and the turn, and you had result becoming zeros.
For some of the cases, the argument becomes 0, and that's why we have these points, because the argument was 0 for that points, for those. Here, the axis here is n,
Yeah.
and we plot phi n with respect to n, and for n, for instance, equals to 0, 1, and 2, we obtain, or we can show that it is 0.
Yeah, I didn't understand why it was 0.
Okay. Let's look at it one more time. Are we agreed that C0, which is for n equals to 0, I mean
number, so there's no.
It's a
imaginary
positive
part.
real number.
Yeah.
So if I put this chart here, in order to reach to the position of this cross, I don't need to move up or down because the chart is on the axis which the cross is. So the angle would be 0. Okay?
Yes.
Perfect. Now let's consider another n. You tell me which one.
No, any positive number would always be 0, right?
If inside the parenthesis you have any positive number
Yeah.
from 0 to infinity,
Yeah.
then the argument would be always and always 0.
Yes, but
However,
if I put minus.
yes,
1,
if you get any negative number here, real negative number, then you are sitting in the other side of the axis.
Yes.
For instance, here and here. And this chart, in order to move or reach there, needs to turn
Yeah.
5 degree, to reach there. And that's why I have, for instance, pi and minus pi here.
Yeah.
Again, if
But
you
you're putting in minus, but because if it's the angle, pi and minus pi is the same.
but you can also
Right.
move the other direction.
Yeah. But it is the same.
Yeah, but because we want the mirroring with respect to
Oh.
origin, then we should move another way. But if you don't remember this argument, I again encourage that you refresh it from your notes or internet. Yes, but maybe I can also do this for you. I think should be a common line for finding the argument as well. Now, I have 2 more slides, and then we go to the maple. These are just definitions. So if you want to find the mean effect, or sometimes we call it mean power of a function or a signal, we have a formula for it. But in order to obtain the mean effect, first we need to identify or define the instantaneous effect or power. I think you have heard this term in one of your electric courses probably, when you have voltage, current circuits. I'm not 100% sure, but I think you have heard it. So it is almost the same. For any signal or function, the instantaneous effect or power can be defined as this small p of t equals to absolute value of f of t to the power of 2. If f of t is real, like this example we had, you can use this formula in the middle. But if you have a function which is not real, it's complex, then this absolute value to the power of 2 would be always and always f of t multiplied by complex conjugate of f of t. So how we read it? F of t multiplied by complex conjugate of f of t. Can you remember what's complex conjugate?
Yeah.
Perfect. If any of you doesn't know, just let me know. Yes. Is it clear? Okay. And simple example is, for instance, assume you have a complex number of 2 plus 3j. This is your number, and if you want to find the complex conjugate of number, it will become the plus becomes minus 3j. So this is the complex conjugate of the first one. And for f of t, you can use the same concept. So when you have this small p of t or instantaneous power, then if you put it in this formula, then you have the mean effect or power of the signal. And here I'll just replace p with this absolute value of t, so they are the same. So this is how we obtain the mean effect or power of the signal. The mean means average. So when you obtain the mean effect of a signal, somehow we obtain the average of the signal over the period of the signal.
Okay.
Yeah.
Okay. Okay.
This is the last theorem, which says that for a t periodic function, which you can write it in this format, you can do the rough approximation and have this Fourier series, then the mean effect for this t periodic function can be be obtained by this new formula, which is depends on Cn, the coefficients you obtain for this Fourier series. I have one more. I think that was also here. This is the last one. Which under what condition we can ensure that the Fourier series always converge to your original f of t, as far as you have the piecewise differentiable function, then always and always they will converge. So just keep in mind, it should be piecewise differentiable. Then the series converge also. Yes? Piecewise, I think in Danish it's called stykkevis. Yeah. And then of course differentiable, it means should be you could apply differentiation for each piece for stykke. Yeah. Okay, now if any of you could download the Maple file, which I haven't learned, and borrow his or her laptop to me, I really appreciate it. You have it? Just download the file and open the Maple. Oh, you did it. Perfect. Thank you. Is it? Oh, I don't have the. Let's see. Maybe it works. Does it? This one works? I don't know if you looked at the Maple help file, which is learned before or not. But here is a summary of how you can use Maple to do the plots for range of -4 to 4 for you, for t periodic function and so on.
Can you turn off the light again?
You cannot see? Is it good?
Yeah.
So, assume I have a function which is periodic from -2 to 2. You can see it's periodic from -2 to 2. And it's defined as this formula, 2 times t minus half of t to the power of 3. How you should define this in Maple? First, we always define periodic function as a piecewise function in Maple. So you can see I wrote that f of t is a piecewise for the range of -2 to 2 of t, and then comma the formula we have for f. If you have multiple line for your function, again, if you look at the Maple help function, there you can see how you can define for each different intervals the values of function you have. And of course, with the plots, you have it for one interval. And now, what I want to do, the goal is that instead of having one interval of -2 to 2, I want to plot it for 3 intervals. So now I want to plot it from, for instance, for -6 to 6, okay? So this is what I want to do. In order to do that, first of all, in the first line, I defined f of t, so I have it. So first, what I do, I rename it and call it f of t, and rewrite my function f as a Heaviside function. You have learned it before in Laplace lectures. You can write it in a paper. So I just use that, which I had in a paper, and write it in a Maple now. Because f of t is only from -2 to 2. And if you do that, exactly you get the -2 to 2 range here. So now I have f of t in a Heaviside format. So, I need to, please take a picture of board number 5 if you have not done it already. Good. So now I want to repeat the same plot or function for two other periods. Let's see how we do that in Maple. So the original interval I have is -2 to 2. Let's assume this is the correct plot, but I have this, okay? This is one period. And now I want to do the same period from 2 to 6, for instance. In order to have, the 4 is also here, in order to do this plot here, I need to shift my plot 4 units to the right. If I do 4 unit shifting to the right, then I have this one. Let's assume they are identical. My drawing is not good. Okay, so for this one, I did 4 unit shifting to the right. In order to get it in other side, to -4 and -6, now I need to do 4 unit shifting to the left. So, something like this. Am I right? So 4 unit shifting right and 4 unit shifting to the left. So now that's why I called a function g, which is consists of origin of f, which is only from -2 and 2, plus f of 0, which 4 unit shifting to the right, and f of 0 with 4 unit shifting to the left. So now, if you do that and plot it, you can have the 3-period function. So always and always you need to define f and then have it as a Heaviside function, and then identify how much shifting you want to do for a plot. It is 4 unit, 5 unit, and so on. And then you do this for a plot. And of course, you can also obtain C0 and Cn there as well. But I will not go through these. But here also try to plot the amplitude. So you can, I want that you play with the amplitude and phase spectrum first yourself, and then ask me if you have any question in Maple. Because it's challenging, and if you don't do it now, in exam you will be stuck. So try it now. I think that was all for today. I don't have any